Thank you, Lola. Thank you very much for the invitation, and to the School of Architecture here. It's a real pleasure to be here. I've been admiring your program for a long time, and I'm excited to finally see it in the flesh. And I also want to thank Barbara Miltichenko, I think is how you pronounce her last name. I could be very wrong. But thank you both for the smooth transition. I really appreciate it. So today's talk, when Lola first invited me to come, she really wanted me to talk about the ICE projects because specifically it is a bit of an unusual territory for architecture, and I of course am sympathetic to that. But I thought I would try to start off the talk with a bit of the origins about what I'm actually concerned with. I mean, ICE is a vehicle for some of the concerns and interests and the provocations that I'm focusing on in my work, but I think that there are questions that extend beyond ICE and beyond the kind of paradigms of this is what I'm doing and this is not what I'm doing. I think what I'm interested in are the things that connect those bits and pieces, and I will actually be talking about that. So, yes, as you know, or may have heard, I am, of course, calling from Winnipeg, and I don't need to explain to you about Canadian winters. You're very well aware of all of that. But I will explain the fact that duration really does matter. And when you have climates that are, in fact, extreme and reaching down into the depths of the minuses that are meeting Fahrenheit and Celsius together, you actually start to see phenomena. And I think that that's really exciting. Honestly, I moved from Philadelphia. I'm an East Coast United States native. And when I landed in January 6th of 2005 to Winnipeg, I was amazed. I had never been in a climate like it before, and I had started to see things with fresh eyes, whereas most Winnipeggers were ready to just get home or to work. The river trail in Winnipeg is emblematic of the nature of Winnipeg's spirit to embrace winter in a way that is in fact about enjoying the unique advantages of seeing the city from the riverside. The city was not meant to be seen from the riverside, and yet it is. And in the wintertime, the Warming Huts Festival, of which you've probably heard a bit, and of course I actually went to the beaches and saw some of the structures that are being built out there, so it's really exciting to see winter being embraced here as well. But then you start to see formations of the environment itself. When you start to have interest in the idea of form and matter and material and energy, suddenly you start to recognize that the sights around us that are in fact all around us constantly become so commonplace, but at the same time, if you look close enough, you realize that the structures are actually pretty extraordinary. Like rings of a tree, they tell you about how they were made. It's sort of like a 3D particle printer in reality. And the idea that snow can in fact accumulate and create forms and geometries which are not in our intuitions about what shapes they should be making. Large cantilevers extending and showing that they're capable of having high capacity of tension for their size. And the undulations, which at some size seems arbitrary and in fact may be annoying when you're trying to walk through them. But in fact, when you look more carefully, you realize that the patterns are speaking to systems that are much bigger than us and in fact much bigger than our sense of awareness. And that's something I'm deeply interested in. I think that in architecture, it's important to recognize when our intuition is not firing on the mark. When we start to see forms that in fact don't speak to the things that we understand about how to build, or in fact maybe that we understand how they were made in general. We understand, of course, that snow is an accumulation of humidity, cold, wind, and aggregation and entropy all wrapped up in one. But actually, our intuition calls from different places. If we look back to the origins of where our geometries and formal languages of how we draw architecture and how we draw invisible force flow that shapes our environments, we start to realize that in fact there are discoveries and ideas about geometry that are based in this sort of bifurcation of the experience of formal representation and the realities of complexity and natural form. So, for example, Hugh of St. Victor spoke about the fact that he said that there are two parts of geometry: the theoretical and the practical. The theoretical is that which contemplates proportions, quantities, and their measures by the speculation of the mind alone. The practical is when we measure the unknown quantity of something by the experiences or the experience of the senses. And I think the experience of the senses is a really important part because he's suggesting in a lot of ways that we don't actually have the full capacity to touch all of what geometry is actually calling from with all of our senses. There was also the idea that Jordanus Numerarius, who was starting to take these ideas of geometry and constructing mechanical models and developing ideas of invisible force flow being represented by vectors and the idea of equilibrium. So one of the origins of this idea of equilibrium is incredibly important because it suggests that things come to rest. And that idea of rest is probably the way in which maybe the students here or most of us have been taught about structures, which is through statics. And statics are calling from the origins of this idea of mechanical systems that are in fact at rest. And it wasn't until about 1866 when force flow was represented in more than just a singular linear vector, when force flow suddenly became more like a current, a river, sort of a direction of wind that in fact is not singular, but in fact a series of vortices that are moving through space and through matter specifically. So what we see here is in fact Carl Kuhlmann, who's suggesting that the arched patterns in the section of the femur, the human femur on the top left, is similar to, in fact, the shape and geometries of the crane that he was designing, and that the forces moving through them would develop something called principal stress lines. And the principal stress lines are, in fact, a sort of a simplification, a reduction of these force flows and dividing it. And it's saying, here's where compression is, and here's where tension is. And in fact, most times they're at 90 degrees from each other, and that's how we get shear, if you look at diagrams. So these ideas, of course, persisted, but the thing about force flow is that it was soon discovered, or previously, of course, by Robert Hooke, but Sir Christopher Wren, who knew Hooke, recognized that these forces could be used as a geometric tool for design. And of course, that in itself is something that Gaudí took through his stereostatic modeling and the three-dimensional constructions of using it as a design tool. So suddenly force flow is migrating from this thing that is representational, that is about being worked out in plan on paper as a premeditated planning for the construction of a static object, to something now where force flow is a dynamic property, something that's in fact able to be worked with through dexterity, if you will, for the architect or the designer in this case, to be able to adjust and respond based on the physics of what's happening, the physical computing of the materials that he's working with, if you will. Ivan Sutherland at MIT developed Sketchpad in 1960, and this was the first time that this idea of a moving modeling system for force flow could be understood for designers, but specifically through computation, so moving out of the physical and moving into the digital. And of course, in between, we have people like Frei Otto and others. Frei Otto was around this time and later, who started working with physical modeling and so forth, but actually Sutherland was the first person to start to put it towards computation. And why that's important is because computation allows us to think about this amorphous phenomena of force flow and to in fact give it an association of size and measure and scale that we can actually then relate to the practice of design and construction. But the origins of parametric design and the continuation of how parametric design actually was evolved and adopted by the design profession was in some ways limited in scope, because parametricism, while it is about behaviors and the associations of things that are linked by parameters, you know, of course, the origin works of Greg Lynn and so forth, who is one of the grandfathers of, we'll say, modern design and parametric spheres, is that the objects are in fact shaped by digital physics, but then constructed by industrial modern techniques. So the work with, in fact, these new origin materials or tools and machines, if you think about it, are actually still using the same brute force that we've been using for over a century to be able to construct and shape matter to our will. So all kinds of materials are in fact becoming shaped by the same methods that we've been using, which is in fact the single-axis machine. It's the same thing that's been using for cutting plywood, for the same thing as rolling steel off of a mill, And so these prismatic sections and shapes are in fact the same tools that are being used to rotate the gears to move a robotic arm, to move the printer for the 3D printer, for cutting lasers, and of course for machining. So when we see projects like this that use parametric design to come up with pretty fantastical shapes and unusual geometries, which in fact may be structurally efficient once they're built, do not actually take advantage of that parametric behavior during the act of construction. Nor do the materials themselves take advantage of the efficiencies that they offer through their own natural parametricism, the way that they in fact respond physically to force and action. And all of these ideas are actually linked to the origins of the division between the designer and the maker after, for example, the arts and crafts movement, when we started moving from the conceptual instruction to the empirical, the actual as-built condition. And that rarely was the thinking and the movement of the gesture of ideas moving in both directions. It was very much in a singular direction. And that hasn't changed a lot, actually. While there's, of course, a wide gamut and scope of work and research being explored, there is still this implicit idea that the designer designs and materials follow. If you look here on Block Research Group's projects here, this is experimental thin shell masonry vault projects coming off of the traditions of Guastavino. You can see that the design process coming to the materialization process is linear in nature, it's directive in nature, incredibly efficient because the tools that are being creative help to facilitate that workflow. But what this does, again, is still treats materials as passive actors in this physical condition that is actually something that they can arguably participate in. Ursula Franklin is a favorite of mine. I really appreciate her perspective on the idea of technology. She gave a great Massey lecture on CBC related to that issue and wrote books on it. But she says something about technology, describing it as a multifaceted entity. It includes activities as well as bodies of knowledge, structures as well as the act of structuring. Our language itself is quite poorly suited to explain the complexity of technological interactions. How does one speak about something that is both fish and water, means as well as ends? And I think this is kind of what I'm trying to get to, which is this idea that tools are in themselves not wrong or in the wrong direction. But in fact, the way that they are being designed and utilized is often preempting the participation of other forms of knowledge and information that can infect and participate in our design and, I would say also importantly, the construction workflows that we engage in when we start thinking about new forms of architecture in terms of efficiency, geometries, and architectural expression. So I sort of put this forward, that in order to achieve a holistic approach to technology, we must first attempt to confront the unencumbered and natural state of material and energy systems, unmediated and unrestrained by the limits of our current logic. And I think that this is something that I don't know if we're very good at. I certainly am not great at it, but I'm trying with these works which are trying to invite materials to participate and suggest where we are in fact falling short in understanding the greater extents of these logics. So I put forward 4 ideas that sort of embody the approaches that I'm attempting to explore at the University of Manitoba. Mythology, I think, is something that we should be paying a little more attention to. So Marcia McLuhan describes that myth is a contradiction, or excuse me, a contraction or implosion of any process. At the instant speed of electricity, it confers the mythic dimensions of ordinary and social action today. We live mythically, but we continue to think fragmentary and on single planes. And I think that Marcia McLuhan is reminding us in a lot of ways that despite our capabilities, we can't lose sight of the fact that there are in fact mythical qualities to what we're doing. Even just flying here to Waterloo is still mythical in proportions to the way that people would live 100 or 200 years ago. I don't think that we can rely strictly on basic knowledge, on the conscious and intellectual comprehension alone to guide awareness. I think that we have to allow ourselves to invite our unconscious and intuitive comprehension to participate in the design process, a form of intelligence that's not bound by the narrow constraints of reason or the scope of comprehension, that we have to work to shape our intuition as much as our conscious intellect. Luigi Nervi, of course, the preeminent engineer, would speak about this a lot. He would actually speak about it to students and young engineers, and he would describe the fact that as soon as we codify engineering and we break up structures into their constituent parts, and we give the example of how we can solve for the equilibriums of structures through these constituent parts, we actually lose the soul of the project. And he talks about how this actually affects our intuition, and structural intuition is actually one of the most, I would say, applied versions of intuition that are in the industry, I would argue. Structural intuition is incredibly profound. If you talk to any structural engineer, they will absolutely acknowledge that, or they should anyway. So he would say that although we observe and see innumerable examples of form-resistant structures in nature and everyday life, from eggs to women's hats, that is, structures whose strength is a direct consequence of the curvatures and corrugations of their surfaces, resistance through form is not a part of our heritage of study, analysis, or representational traditions. As a result, it's not yet entered the set of static intuitions from which we draw to design structures. In other words, he says, we're not yet used to thinking structurally in terms of form. And I'd argue that's still the same today. It doesn't mean that we don't understand how structures support form or how forces move through form. In fact, we can diagram it very well. We're getting incredibly good at it. But has it yet penetrated our structural intuitions about how we approach architecture and structural design? There are synergistic ecologies amidst, whether we acknowledge it or not. And I think it's vital to recognize that the natural systems we are based on are based also on an ecosystem of information and knowledge that is distinct from ours. While our sphere of knowledge is based on it, we are incapable of dwelling in it for long. For the depth and synthesis of it is beyond what our structures and logical thought can rationalize. Its majesty has become too apparent to us and is often mistaken for a result of our making, often through the act of giving it names. Its sources are deep in the rivers that spring up from it for us in a variety of distinct forms like behavior, structure, growth, form, texture, etc. But the implicit nature that it connects with, these things remain deep underfoot and intertwined by nature. James Clerk Maxwell discovered the underlying unity that links three distinct and separate phenomena that previously were thought of to be, of course, separate, that being electricity, magnetism, and light. Previous to Maxwell, these phenomena were studied independently. They were seen independently. But because of his recognition through his physical experiments, and here we see three-dimensional modeling of thermodynamic surfaces, and some of the sketches he used to show that, we're starting to show energy flow in ways that we're linking phenomena, which in itself is a really profound thing to recognize. And that's the kind of thing that we have to begin to recognize is not just connected to experiments bound inside of scientific laboratories, but in fact surround us constantly and are in our buildings. The fourth and final point that I would make is actually, right before that, Michael Faraday, who preceded Maxwell, he contributed to a lot of the foundational theories that Maxwell spoke about, proposed something even more extraordinary. He suggested that through his lines of force theory, that all of reality is made up of force itself. So let that sink in a little bit. Fourth point, I would say, is dynamism. Much of our energy is expended to attempt to control dynamic flows of growth or decay, order and disorder. We need to move from static structures that resist this inevitability towards systems and structures that can adapt and in fact thrive on this flow of energy and materiality. And we can think about this in the terms of the fact that the role of designer is one in our origins of conquering vast challenges presented by natural systems, being the weather, environments, and so forth. We use the incredible efficiency of minimal structural systems and a dynamic behavior that let us engage with those to, in fact, stay afloat. We, of course, moved into systems of static thinking, which I briefly described, and are now starting to recognize, because of computational prowess and awareness, that, in fact, quantum mechanics is ironically starting to harken back to those origins of indeterminacy and starting to think about the ideas of things like superposition and parallelism, where the indeterminate conditions of working within computational systems are, in fact, reallocating or changing our role as designers to be participants within the flow of something we're not in control of. So something that essentially means that it's a system for us to participate in, but not, in fact, to dictate or to predict. So quantum computing is ironically hearkening back to the origins of what would say is the genius of physical computing, which is just materials themselves. So now we arrive to Winnipeg, and these 4 concepts, I think, require us to learn how to be comfortable working within systems of deep complexities and dipping in and out of comprehension and control, but always remaining flexible and open to the feedback and influence of the material and energy systems that are within the design projects that we're developing. So kind of a simple way to describe that is that in CAST, the work that I take part in is, instead of, we'll say, I was describing through traditional forms of more, we'll say, contemporary parametric design and fabrication processes where an idea is had generative from a person. The computer helps to produce a form or a system. We then have to break up that form into constituent parts, and then the question becomes how to put it together and how to maintain that origin of ideas. And in CAST, we kind of work in the opposite direction, which is, in fact, taking a material, playing with it, pushing on it, seeing what it does, and then developing something, and then the idea is what to do with it. And I think this is really important, because the research I'm showing here is not about replacing this. It's about looking for alternative ways to think about developing structural systems, working with material and structural behavior and energy flows that we're inevitably confronting anyway. So there are some basic tenets that I would just put forward that are based out of this work. So that I'm interested in congruent design and construction methods that stem from material behavior. So the idea of congruency between design and construction is critical, or else there is this translation that's required to, in fact, adapt construction to speak to that initial design intent, which is that industrial modern origin. Structural efficiency through actively formed material systems, so trying to treat materials as active participants, and when they are activated, they actually become stiffer and stronger, and in fact offer new geometries for us to play with. Utilizing material deformation as an advantage and avoiding the assumption of static determinacy. Open and lateral study of a wide range of materials to discover universal behaviors and methods of working, and that speaks to that kind of idea of those ecosystems that are connecting all of behavior together. And abandonment of the predetermined or ideal designs in exchange for negotiation between material behavior, design intent, and constructability to arrive at unforeseen and open-ended results. So, as Lola had mentioned, I've been doing this now. I arrived at CAST in 2015, and since then have been honestly playing. Because the way I was raised and my structural engineering backgrounds did not prepare me well to actually understand material behavior. I can design and predict static systems. I can understand, generally speaking, what's going on inside materials, but I have no idea how to play with them. So by starting out with materials like plaster, we realized early on that, in fact, the liquid to solid material and nature of things like plaster, which cure and crystallize like concrete does, it doesn't go through phase change like ice, for example, to be able to go backwards and forwards, are able to be analogs for other liquid to solid materials. So when we play at a 1 to 10 scale, you can play and predict at a full scale. Wood systems were other materials to experiment with, and they are their anisotropic properties, their ability to have grain and orientation and bias and histories from what they once were as a tree and what they are now, and their desire and memories of that coming back during the construction and making, all contribute to the idea of flexibility in wood systems and what those can generate. The bottom right project was an installation I did with Ronnie Araya, who's an architect in Montreal, and This structure evolved out of a negotiation and conversation between us and the structure, and hammering these thin strips into the cracks of the wood structure above us and the floors, and starting to weave downwards together. Fabric has been an incredible partner to work with, and it's been consistent throughout all of the work there, because fabric is quite expressive. The material systems that's offered allows for things that are working with projections, which allow for a sort of a reimagining of the ideas of perspective and Cartesian projections of structural forms and shapes, and how that can be deformed by projections. Wax came about as an experiment to play with ice inside. How do you work with liquid to solid materials that can reverse cycles, and how do you work with it at a hand scale? So what this is a modeling machine that uses engine block heaters underneath it to melt paraffin wax, and magnets are those orange pieces, and the string are all ideas about the actions one would take as a designer to shape structural forms, and the wax itself is a good analog for how one would apply another liquid to solid material, like, of course, ice or water or concrete if you use things like shotcrete or you trowel it on by hand. And then photographing them afterwards and starting to look a little bit more carefully at what they present as an after effect, the result of these actions, I think starts to speak a little bit towards the sort of the way that these structures present themselves in the world as archetypes and as architectural language that we are interested in. I'm going to focus specifically on two materials. The first is fiberglass. And the way that I began working with fiberglass was literally just trying it out. How flexible is it? What is it like? And this is fiberglass rebar. So this is typically used in materials like this and in very expensive projects where rusting, spalling is predominantly the failure mode, and it's expensive to repair things like bridges, for example, but fiberglass rebar does not fail the same way. It has an incredible capacity for tension, but also elasticity. So by letting go of the material, we begin to sense in the origins of that geometry definition the way that the material behaves. But this, of course, is not a new system. This is, in fact, hearkening back to those origins of efficiencies and the ideas of creating complex structures using minimal material, minimal construction energy, and highly efficient space creation. So the question about how to translate that starts to speak to the practice of design and then construction. So this animation shows how the material system begins to do things that I would describe as self-organizes. That these geometries, based on the way the bars are in fact laid out, where they are connected, and where they are put in place, begin to organize themselves to larger geometric forms that then speak to the capacity and potential for space creation in terms of architecture. And then we start to visit ideas like failure. And earlier I was speaking to some of the students here about the idea of breaking. And I think breaking is a lovely term. It's one that I actually don't use a lot, but I think what it does speak to, and I think that we discussed this a little bit, is about that threshold of when things begin to reveal themselves and what they're capable of. So failure modes for static structures like we're in, failure modes might be described of course, as catastrophic, but also deflection of maybe a quarter of an inch or something like that, a few millimeters. But structures like this do not speak to that. So we have to reorient ourselves and say, well, what actually are we making? So one of the early experiments was using this for a project which was based on traveling to 7 different remote communities and working with the community members in these remote communities to bring modern art to their venue. So what this was carrying 60 bars of fiberglass rebar on a 1967 Airstream trailer and showing up with community members and erecting different structures in each community based on the same bars but with different patterns. And what we're looking at here are these temporary art gallery venues where they were programmed in lots of different ways. But this was the first time I began to understand about the relationship of the role of the designer as a curator rather than one that dictates the form. And this idea about synergies came to pass in a very profound way when I was developing a workshop for Rochester Institute of Technology where they wanted to build a prototype of one of these structures for their winter festival. And I was trying to figure out how do I send the bars I can't be there early enough to prefabricate the structure for the students. In fact, it was going to be run as a workshop, so I was going to send instructions for them to receive them and to, in fact, start shaping these structures before I got there. At the same time, Professor Mark West, who's one of the preeminent experts in the world on fabric-formed concrete structures, who also founded CAST, and I worked very closely with for over a decade. He was working on a bench at the Women's Hospital in Winnipeg, downtown. And he was working with hydrostatic structures. He was trying to fill essentially sacks of formwork lining, which essentially is a landscape fabric, and trying to figure out how do we make sections of the bench, you can see in the bottom left there, and join them seamlessly so that the shapes and the geometries of these curved benches in fact meet when I'm casting them separately. So he was actually starting to have conversations with engineers around the world and realizing that in fact the shape that his bags were making were the exact same shapes that I was working with in model form. That the form of the shape of the purely elastic geometry, which is called elastica. So elastica is an actual shape, not just the name of the behavior. These curves that my bars were making were the exact curves being made by his hydrostatic water-filled sacks. So this is a model of one of his structures. This is the end of one of his benches. And this is an elastic bar making the exact same geometry. So the sudden correlation and recognition that we were working with the same physics, but through two radically different building systems, two radically different approaches, and two radically different ways of our conceptual thinking, were in fact co-aligned. So I made these instructions. I found out that basically if we were to break it down into simple steps and make essentially A-frames that had a bend between them and then pull them together with rope to just get them prepared, that effectively we could just suddenly adjust slightly some of the connection points and the geometries would begin to splay, and we would have a bit of a library of forms to play with once we arrived. So the students worked hard to struggle with this very strange spaghetti-like structure that I sent to them from Winnipeg. Worked on positioning it in the right positions, used gear clamps and electric drills to put them together, but were able to erect these very arguably quite precise structures with very little experience because the work was not about designing anything. It was actually about finding the connections where the material behavior could self-organize to what was being intended. So we drove rebar, steel rebar as foundations into the ground and began to organize the geometries of these bars into different positions so that we'd be able to get an array that would lean towards the tunnel system we were trying to make for the Winter Festival. And then we began to install fabric on it and tailor it for the site and to allow people to pass through it. And lights and images were projected on it for other occasions. But the geometries and forms were something that were arrived at as a collaboration with the students' ideas, how the fabric should be applied, and then, of course, the geometries of the bars that were sent. The second material, which I'll talk about a couple of projects, is, of course, ice. So being located at the centroid of the North American continent privileges us from having climate being moderated by large bodies of water. And traditionally, fabric-formed ice projects have been happening for a very long time. You can ask any of our elders that still used to use laundry outside, and once in a while we're lucky enough to still see it. But of course, people like Heinz Eisler also experimented with the idea of fabric-formed ice structures in his backyard and started to do so more formally with pneumatic structures and so forth. But Heinz Eisler was one of the first people to begin to experiment with the idea of parametric construction methods. That's what this is. So the idea of self-organizing material systems is now translated from the idea of making small physical models to making them at large scale. And that's something that I think is really pretty powerful. Here we see some of the work by Arno Pronk, which you see some brown ice. That brown ice is what is called pikecrete, which is an invention that was spurred on by World War II when the British were trying to figure out how to make an unsinkable aircraft carrier so that they could in fact land their planes that were dropping torpedoes on U-boats. And there was a proposal put forward to construct a giant aircraft carrier out of ice. and the proposal was taken so seriously that there were experiments done in Edmonton to try to refrigerate large blocks of ice to float them. It never got built, or I'm sure you would have all heard of it, but it is still pretty profound because the wood chips that are making that brown color are making the ice as strong and durable as concrete. So some of the early experiments that I did with ice was the curtain wall project in the top left, which simply was taking ping pong balls and tying them to the inside of hoodie material, doing a simple 2 A-frames out of wood, a bar across the top with pulleys and ropes, and raising the fabric, spraying it with water, and making a little bathtub to catch all the water to make a base. And we used it as a projection screen for the Atmospheric Conference in Winnipeg. I then ran several classes to work with students to explore different ways that fabric and ice could be used, because this was something that, again, I was starting to begin to explore myself. And you can see on the bottom left, Vortex is a project that was created by using the bridge overhead as the scaffold system and hanging rope from it and pulling up on the points that were made there. And on the right, the same project, students created columns and put internal struts to deform the geometries, because those deformations actually give structural stability more than just create fun shapes. From there, I worked on projects like Cocoon, which tried to integrate and synthesize the use of fabric-formed ice and the bending active frames of the fiberglass rebar to create that tunnel system. The first project I want to talk about a little more in depth is Fabrigami. So Fabrigami was also for the warming huts in Winnipeg, and we decided to work with the idea of origami as a self-organizing building system, and how the structures themselves act as beams that are inclined and leaning on each other to convey forces across them. But from all the origami forms that we've seen in our histories, there have been very few that have used the actual origami nature, the self-organizing principle of structural order through folding at a full scale, because the material systems they're using are, again, out of these origins of the industrial modern shaping through force. So we tried to combine the idea of fabric-formed ice and origami structures. And the first work was figuring out the site, which was the bridge. Here you can see in the yellow. This is the bridge. And this is a counterweight, a giant concrete counterweight to, in fact, live and raise and leverage the bridge to make space for the boats underneath. And from there, we found a basic origami design which is structural in nature. Not all origami is, or some origami is simply behavioral and dynamic like a mechanism, and some are static structures like this one. And we began to work with digital tools to figure out how to work with the edges of the folds as a way to work with the linkage to fabric. So if we can control the parts where fabric is being pulled taut, and we let the fabric self-organize in the valleys, then we can in fact make a building system that's doing the folding for us. So we began to stitch out and lace out the folding for the lacing of the fabric. You can see here of the top right, the pulling tight, and then the top left, the pulling tight of that fabric creates the general outline of the origami structure. And if we lay the fabric on top of that, the fabric hanging from it will actually make the cavity system. So we began to explore this in a range of typologies, forms, and evolutions. We had a final form that we ended up developing, making it a bit asymmetrical to make space for seating. We began to think about how to make an upper cable net system, which is this system right here, and then a secondary system for grab cables. Those grab cables would pull the whole thing up like a marionette, and then anchoring the fabric down to the bridge deck itself. We worked with the loading to be able to think about the size of the steel cables and the rigging, breaking it up into kind of constituent parts that we could have prefabricated. And then we worked in our center space here. That is our largest space that we have on campus, at least in the architecture school, to lay out the cable net and then to put the fabric on top that we sewed and cut the holes. Created some custom-made giant ice calipers to grab the bridge, as you can see on the bottom left. Quite oversized, but fun antiques to have around afterwards. And the construction, which is always the fun part. So essentially we laid out the construction here where, so you can see the upper cable net is in place. That's the part that's shaking a little bit. Then the vertical cables that are the grab cables came down through the holes and grabbed the net and then went up and down through. So it goes all the way up and through. And then from the inside, we can pull up like hoisting a sail, essentially, till the whole structure became volumetric like we were anticipating. And we would then align that with our measurements to see how close we were getting. So the act of making it was actually a revisit to the question of design. So the cyclical process was actually thinking about that. And then these moments where you stop and you realize, wait a minute, I'm building in foundations, and the foundations, which are typically piles, are suddenly piles in the sky. And what was interesting is that you can't also fully predict the geometries that the liquid and the fabric will want to make. And so as we're watering it, and the temperature is about minus 20, 25, the shapes that it's starting to make are surprising, right? You have moments where they're quite smooth, as you might have expected, and then there's spaces where they're incredibly complex and many, many corrugations on the shell system. So in the end, we had this as a larger geometry. It was not about as a strict folded plane as creases, but more about the larger organization of the shells, the structural shells. And because of the double curvature nature of the fabric, which was slightly elastic, the shell forms in between were stronger than if they were folded planes. So we decided the only way we could really test it in a safe way, because this is a public space, is to essentially loosen the cables. So these upper cables, if we loosen them, these are turnbuckles on the sides. If we loosen these turnbuckles, these grab cables will loosen as well. So that's what we did. We loosened those bit by bit, quite nervous and curious to see what would happen. And here, this is an image of it after they were loosened. So there's not a lot to see before and after. The cables and the shadows are the only things moving, but the structure remains still. You can see here the cables letting go. And us deciding, well, it hasn't moved yet. I want to hang on it. So we did, and we jumped on it, and we grabbed, and this is Jason Hare on the left. He's a collaborator of mine, and that's me on the right. And this is a 1/4 inch of ice. A 1/4 inch of ice in average on the whole structure. It's holding up 2,100 kilograms, so about 5,000 pounds of load, of just dead load of water and ice. And our dead loads of 180 pounds each or something like that is not going to do much. But it was still extraordinary because this is, again, working back with this idea about feeding our intuition. Getting a sense, banging on it, touching it. When people would skate through this, they would touch it with their bare hands. They were wondering what the thing was, what the material was. And it defied a bit of expectations. And I think that's really a lovely thing and kind of something we could be doing more of. The last project I want to describe is Ice Bloom. And Ice Bloom is the culmination of the work that is speaking to a lot of these origins, and it is the subject of my PhD, which builds on essentially these two building systems. So bending active frames as a skeletal work, as a sort of a guide for the fabric form work, and fabric formed ice shells. Fabric formed ice shells as a fabric formed ice shell, and also as an analog to other liquid to solid materials. So it stands in for both. So Ice Bloom was a collaboration I did with Michael Cox and Professor Dr. Sigrid Adriansson at Princeton University. And the work that they did was to help organize and describe the principal stress lines on a simple hanging shell, 4-pointed dome. The red you see are the compression lines, the blue is the tension lines moving through the structure. We then began to work on this collaborative approach. We're saying, well, okay, we now have to introduce ideas of construction. And that means these points cannot be converging to infinitely small loci, which are just impossible to make. So we have to spread them out. So the shapes began to change a little bit. The geometries of the principal stress lines are such that they are, in fact, as I mentioned, currents of flow of forces. So the currents don't generally change a lot when you do behavioral shifts or formal shifts like this, but they do, in fact, make a difference. These are the spaces where we made size differences. And then Dr. Adriansson and Michael Cox, who was doing his thesis project on this project, we're doing analysis computationally on the behavior and the performance of these shell structures, saying, okay, well, how do we in fact deal with the fabric? If we ideally model it as a smooth eggshell, which is what the top left represents, we get a stress distribution as you see in the top right. If we let the fabric sink into the cavity spaces between the bars, it makes this kind of what I would call an ice tray configuration of the middle structure and then the right structure on the right-hand side there. And then if we do this, what we call this pedal approach, where we separate the tension and compression bars. We drop the tension bars down with a sort of a spacer, and we let the compression lines actually run the full length from the foundation all the way up to the oculus. what ends up happening is that you get continuous compression zones carrying the full length and integrity of the structural system. And what's even more interesting is that if that's the case, then that means the water itself will self-organize to those valleys. So as we're spraying, the material finds its place where it needs to be. And when it collects in the valleys, it makes three-dimensional beams into the three-dimensional compression zones that force flow is moving in. So how to build it? So then we started to say, okay, well, let's break it up into 4 parts. This is one of the petals. We sized the bars based on the bending geometries. That's what the description and the thinness and thickness of the lines are. And then the first question is, could elastica forms, these are piano wires but also act in the same way before they hit the plastic range, can they make the same shapes? And in fact, they could. So that at the model scale, we see it is possible. We then worked on prefabricating. We made aluminum spacers. We made custom laser cut aluminum spacers to separate the tension and compression bars. We then began to lay it out on the floor of cast and organize the bars and the geometries. I think, there we go. So you can see the bars are actually pretty pliable. And we had simple marks on the floor. They're all symmetrical elements. So we had a center line and distances off that center line that would in fact make the shapes that we were looking for. And the spacers began to separate the bars from tension and compression. You can see them there. Tension on the bottom and compression on the top. And then we would do a lot of sewing and then move these out to the site. We had these things called launchers, which are these wooden frames that were allowing them to hold each of the bars individually and allow the fabric to stay hanging and sagging between those bars. So we didn't want to have suddenly a transition to flatness when we got to the bottom. We raised it through the middle, and because these are filleted, the project is filleted like a fish in a way. As soon as it gets raised into place, the bars have to be tied together, which proved very difficult. And the structure finally became sort of in the proper geometry, but was not exactly like the geometry we had hoped. We then pulled this fabric over top, which every time we do a project this big, I always describe it as kind of tailoring a suit for a giant, because once it gets on it, you kind of have to deal with the tailoring of it. So here it is when we first pull the sheet over top. Already you can see the bars organizing those principal stress lines. And then we watered it. So we put on about 17 coats of water on this, which produced about 3/16 of an inch of ice. And then once it was frozen, we used an X-Acto blade to trim the edges of the fabric off right at the edge, and the water bonded to the fiberglass rebar, so there was continuity from the fiberglass underpinnings to the fabric itself above it. And then when the snow fell, you can see the shape it was making. In fact, that was what we were sort of hoping for, but weren't convinced it would actually make. And you can see it's not a perfect structure, right? In fact, you see the lip that's popping up a little bit. That looks like by design, but it's not. It's because the precision of dealing with this, constructing with big mitts outside, is not exactly the same kind of tolerances we work with in the lab. So we're beginning to recognize that the construction needs to find a correlation with the way that we have to have a degree of precision to follow the computational models that we're expecting to show. So here's a little bit of the view underneath it. Right after the snow had fallen, I was about to go out there and add more water. But because the snow was in the way, I thought, oh, this is where the improvisation happens. I said, maybe, in fact, I need to spray and mist it. Do I mist it to make a candy coating of ice on top and add a second layer? And then we have maybe a monocoque structure of ice shell, snow, ice sandwich. No, that probably won't work. Maybe I should just make it heavier, you know, melt the ice down with the warmer water or the snow down and then rebond it and let it be kind of a bumpy surface and so forth. And I said, well, I'll just try it. So I started misting one side, did not see anything happening. Went to another side, nothing happened. And the reason why these structures work is because the water coats it. And as it coats it, it gets heavier. And as it gets heavier, it freezes after the shell hardens and it gets stronger. You put another coat, gets heavier, gets harder and stronger. So layer by layer it gets stronger. But all I was doing was adding dead weight because the water was not continuous across the surface. It was getting locked up in the traffic of snow that was on the surface. So when it collapsed, one side fell and the other side, and the whole thing, of course, catastrophically failed. We were able to then measure the ice from the failure that collapsed, the breaking, and look at the geometries from the before and after and try to recognize that as a lesson for improving the structure. Here's a brief diagram of where the thickness of the bars are. I was trying to describe the beams in the valleys. So what we decided next to do was actually looking at a supplementary system that would actually allow us to shape the elastica geometries and provide secondary support, which is using post-tension cable nets underneath the fiberglass rebars. So we started by using small-scale splines, and these traditions have been explored using two-dimensional structures like this. But then we started to recognize and test the performance of this using little washers. And as we started to discover that, in fact, the promise was that they were incredibly strong, the steel cables allowed us to deform and make multiple variations of shape, from asymmetrical arches to symmetrical arches to flat arches to catenary forms and so forth. We then decided to scale up to the large-scale spline, and these wood bars are there to hold it in plane while we're loading it with sandbags. And the results were extraordinary, because what ended up happening is that we realized that the cables were able to, in theory, increase the total bearing capacity of these systems by 600%, which means a lot in a two-dimensional plane, but what does it mean in a three-dimensional system, of which we didn't know? So we, in fact, decided to do that. So we essentially designed a vault, again, similar to Ice Bloom, but that we could build inside and cast. So we also looked at advancing the construction method. So the method one was like Ice Bloom. Up top, you can see we built it in 4 pieces, tried to put it together. Was not actually as effective as we'd hoped. Method 2 is actually looking at taking the scaffold system and building a very simple version of it first to just get the general form up, and then to have markings on the bars and essentially erect it piece by piece. So here's the initial skeleton that went up. And then once that was up, actually putting the bars in place was incredibly efficient. You're just literally laying them down, putting them on the marks, and tightening them with gear clamps. So the initial skeletal form, what's interesting is the design question is, what is the initial form? That's the typology for this geometry. But in any other design, it would be a different skeletal form, and that's what I think is at the next iteration of the design question. So you can see here on the left is a digital model, the middle is a physical model that we made, and then the right is the full-scale structure. Again, you can see variations. This was the digital, and that was developed from a hanging geometry, like a catenary. You can see that the elastic properties of the stiffness of the steel is not the same, so it's kicking the sides out a bit, and the elastic of the fiberglass is also a little bit different than this one here. We then introduced a 3-dimensional version of cables that would follow the bars. So the bars are not straight, so the cables could not be straight if they were going to be relying on those cables, the bars. And what we did was we essentially developed a sequence of erecting the structure. So we prefabricated all the cable systems, installed first the grab cables, which are simply there to reach down and hold the long cables. We then threaded through those, the long cables. These are all prefabricated, so those are done quickly and installed quickly. And then the diagonals took the most time, and those are actually weaving through the whole structure. This is a picture of the spider web of assembly that we were working with. My suspicion is that the diagonals are a bit redundant and maybe overdone. I think we only maybe need the grab cables, which will increase its speed for construction. But ultimately, the question, this is it in the final form. The ultimate question of this is what does this allow us to do? So this research here essentially is trying to understand how to work with these very wet and flexible systems, these high, strong behavioral conditions that are asking and providing areas of knowledge and resource information for us to work with as designers. And what I'm interested in is trying to figure out how that aligns with questions related to the act and needs of architecture and design. So I'm not interested in this as a pure structural system. I'm trying to understand this as an expression of architecture, as a system of space creation, and a way to expand our paradigm of thinking for how we should in fact be building architectures that start to speak to questions about duration. How long do these structures need to be around? How is the act of construction actually something that's a part of the design process and an extension of it rather than a bifurcated part of the work that we end up doing? How do the materials participate and offer their efficiencies? And how can this lead to surprises and maybe a greater degree of pleasure in the work of designing architecture and structures alone? Thank you very much for your time.
I'm just wondering how, like the weather, like the changing weather patterns or wind or, you know, even like sun, like how that affected the ice structure.
Yeah, wonderful question. It sounds amazing when the sun hits the ice and it cracks and pops and you don't know what's happening and you're inside the structure, it echoes. It's a very loud, cavernous kind of space. Of course, above a certain temperature, it'll begin to melt. So anything above -10, indirect sunlight will begin to literally melt. Even if it's -10 out, the sun angle will actually do a lot, especially at the low angle in Winnipeg. It hits a broadside on a lot of the structural shapes. But what's interesting is that when I first started working with these ice structures, the curtain wall project, the first one, we sprayed a lot from one side and we sprayed only once from the second side because we couldn't get to it. So about 2 weeks in, it was -30 for a long time, -20, it was fine, it was standing still. I noticed that actually the fabric was beginning to be exposed on the back side. And I started to peel it away and realized that actually I could pull the whole fabric off of it. And I couldn't understand why that was. Did we not hit it? I swear we hit the whole thing. We doused it. The thing was totally soaking wet. And what it reminded me of suddenly was, in fact, 8th grade physics or science, where we learn about something called sublimation, which is when solid evaporates directly to a gaseous state without melting. It dried out like ice cubes in a tray that's been in the freezer too long. So there's these beautiful phenomena that remind you about what's actually going on. And it's moments like that that, of course, raise the question of, well, is that useful? I still don't know the answer to that, but it's fun to watch and learn from it anyway. Yeah, please.
Well, I'm just wondering, like if it would be possible, whether you've experimented with when you pour the ice on and then peel off. Like, is it possible to take away the fabric and then the ice is like self-supporting, or? Okay.
My suspicion is yes. I haven't done it at a large scale, but that's the beautiful thing with ice is that, look, you can build full scale for relatively no money. Has a minimal ecological impact at building full scale. We don't have to leave materials behind. There's a lot of advantage of working with ice if you're interested in building with something like concrete or any liquid to solid material system. And the thing that's interesting about it is that the construction methods that are developed as a result of that allow you to kind of participate and play, and you can ask a question like that and say, well, okay, then the next time I'm going to just try that out. Or do it at a small scale over here and see if I can scale that up afterwards. You might do something where you spray it and then throw fibers onto it and then spray another layer and embed those fibers into it. You can pre-mix it like Arno Pronk did using the Pikecrete, where he pre-mixed wood chips in the water he sprayed. So that idea of pre-mixing that fibrous tension that you can put into ice is totally something you can do with toilet paper will work. The fibers in paper, the toilet paper, are strong enough to make ice incredibly strong in tension. So you can play in a lot of different ways that you might not have expected, but once you see funny things happen, you can say, well, what can we do with that actually?
Hi, my question is about like the relationship between the intrinsic material properties and that intuition that you were talking about. So you spoke about nature showing us something that we didn't know was possible in any materials. Do you feel like you're trying to get closer to that, like discovering things by letting them be what they want to be? And related to that, or to say it in a different way, do you find yourself making assumptions about structural form that you don't want to make that are hindering your potential, or is that part of the intuition that's making it better? Is that clear?
Yes, 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 and yes. Yes, so the work with all of these materials, these dynamic materials, or expressive, I'll say, materials, is there to work on the intuition side, not as a thing to lean on, but as a thing to kind of round out the education that I've had so far, which has been codified, static-based, structural design thinking, which is not that it's wrong, it's just incomplete. And it's not expressive of the idea of time and the long duration of structural behavior over time, right? You learn about things like creep and modes of failure or breaking, as we were talking about earlier. These things are all related to material properties behavior as a dynamic system, not as a thing that, look in the magazine, here's the thing that's standing, that's the thing I made, I'm very proud of it. But actually, I kind of tried to describe it a little bit, that these are deep rivers, right? I mean, everything we're in is real. It's all happening, it's all connected. We know this, generally speaking, we know this. But the question is, how do we put that to use in some ways? How do we then see if there's a way where that can actually change, even subtly, some approaches, even if we're working with 3D printers, CNC milling, the clay machine, beautiful machine you guys have here for the clay printer. Even general questions, the students were showing me, you know, the just pushing on the thing that was made from the clay. That collapse itself is already speaking back. So it's not that you have to go deep philosophically into these directions to get something from, you know, feeding your intuition. Everyone's learning intuitively about architecture and design generally, and you're all learning about how to design structures socially in intuitive ways, as well as structurally intuitive ways, right? So it's happening all the time. It's just about making that a point in the work, trying to focus on it as a serious line of inquiry rather than it being something I apologize for or pretend isn't happening.
Have you ever kind of experimented with using the temporary ice structures that you make to cast something more permanent?
No, it's a lovely idea though. No, I have not. I've always seen them in them as themselves, and I've always seen them as analogs. But the idea of using the ice as a sort of temporary form work, it's lovely. You should try it out. I mean it. Let me know.
Hi, thank you for the lectures. Very inspiring, very incredible work. My question is just going back to your role at the School of Architecture there in Manitoba. Like, what courses do you teach? I'm just interested, like, you know, do you teach structures? Do you do this in studio? Like, you know, how do you get to, like, it's really inspiring in terms of, like, getting students to get excited about structures and think about it differently. And just wondering, in what form do you pass on that passion at the university?
Yeah, I think it's a super relevant question, especially in a venue like this. I think we need to be talking to each other generally about how do we integrate research and teaching, because it's happening and it's relevant. We structured ours. I teach design studio. It's two semesters long, and I also teach an introductory structures course or construction materials and assemblies course, which I love because you get to them early. I love that. It's really good. And then the end of their career at the thesis level, master's level, where we have what's called an advanced tech topics course. And those courses are 5-week intensive, 20-hour courses where we can dive deep into a research area, bring the students along, and let's ask a really pointed question that's out of the paradigm of normal studio thinking and so forth. So those Vortex projects and other ones are where I brought students along and say, all right, we've got 5 weeks. Let's make fabric formed ice structures. Here's what I've learned so far. I want you to play for 2 of the weeks. Let's make a plan on the 3rd week. Let's get everything together on the 4th week and install on the 5th week. And that's sort of what we end up doing. It takes a little more than those hours, but generally it's not too much more because we've got to respect those boundaries. But at the same time, there's also, I bring a lot of students on, these are all students, almost all of them are students in that section there. And they're repeat offenders. They come back because they want to learn more. They're curious. And so these research projects that we do at CAST, they come in the summers to help out with that, or when I'm building it outside and they're walking by, they ask if they can help, and it's like, sure, sign the waiver, come on by. So there's lots of ways that students can get involved. They're in class and they're out of class, and I think it's partly because I have fun with it, and I think it's important that students also recognize that discovery can be really fun in a consequential way and a consequential scale. So I try not to hide that work so that students are invited to participate. It obviously takes work to do it, so I'm really grateful for all the help, but I think it's part of the education sphere that we're in.
Maybe I'll ask a follow-up question. As you were speaking, I found myself thinking, God, I wish I'd had you for structures in undergrad. And I'm curious, do you find you approach like that first intro course that you were describing, which I'm assuming is possibly more normative building assemblies. do you find that the work you're doing here changes how you teach that? Because I think this is a challenge in almost every school, is how do we teach building tech, and particularly how do we teach structures in ways that are provocative and move
Totally.
beyond calculations and things?
Yeah, it profoundly affects it. I've come to realize teaching, I've taught a course like this for about 10 years now, and I've come to realize that I'm not afraid to deep dive with early students at all in structural discussions and behavior and all of that stuff. I don't keep it nice and safe for when you're old enough, you'll be able to figure this out. No, it's all the same. It's that continuum, right? So in the course where we're talking about basic properties of materials like wood, for example, or how to find resultant forces and things like that, the discussion actually goes deep into that well and then back out and then deep in and then back out. Why? Because I can then very quickly pick up a material, demonstrate it, and show how it's doing that deep thing and doing that really simple normative thing at the same time. And I think that's critical, because if students are taught in a way where advanced thinking, we'll call it, I don't like to call it that, but say that's what we'll call it, is actually something that's held for later, till you get the foundations down, I think that actually perpetuates this idea of the discrete separation of subject matter in our work, in our profession, and in how we kind of need to stay in our silos conceptually and maybe in practice as well. So it affects me because I'm more enthusiastic to kind of even teach the basics, because it's actually closest to that origin than maybe say somewhere around the middle where you're trying to work with envelope systems or something like that.
Last question. Thank you so much.
Thank you very much.
It was really a pleasure.
Thank you.